Hello everyone, I am Mirza Sami, a PhD student from the University of Alabama at Birmingham. I will be presenting our paper, Drone-Based Tower Survey by Multitask Learning. This research was conducted by Yan Lab from the University of Alabama at Birmingham under the supervision of Dr. Da Yan. This presentation is structured in the following manner. We'll begin by describing the problem that this research tackles. Next, we'll describe the challenges inherent to this problem, followed by our multitask learning approach to mitigate the challenges. After that, the training procedure will be discussed. Finally, we'll discuss the performance of our approach at solving the problem. Many industries require towers as part of their daily operations. They require regular maintenance, and before the maintenance work can be done, a preliminary survey must be conducted to determine where to work. Drones have been used in this field to survey towers and determine what maintenance is required. In this example, a drone image from a tower is illustrated. As can be noted in the image, one of the bolts in the tower is missing a pin. An expert inspector can locate these issues from drone image or video frames and annotate these issues by drawing a bounding box around it. Thus, even before tower climbing for repairs, the issue annotations are readily available for supervised learning. However, after training various object detection models using the expert annotations, we found that the detection performance was not satisfactory. We realized that this is because the bounding boxes do not provide sufficient knowledge of the domain context, such as the parts involved in an issue. Moreover, many pixels in a box belong to the background, so are not directly related. This observation motivates us to improve the regular object detection pipeline with the help of another separate task. We first fine-tune an object detection model over part annotations obtained by crowdsourcing, so the model parameters encode sufficient knowledge to detect individual parts. There are several advantages to this approach. First, an average person can recognize the different parts from a tower with proper instructions, so such annotations do not require domain expertise. Furthermore, annotators can precisely mark out the pixels of each part using a polygon, and such strong pixel-level supervision from the mask head backpropagates to earlier layers of a deep learning model to enable highly effective parameter adjustment. In the next task, we further fine-tune the model over the issue box annotations from domain experts. We use the mask RCNN model pre-trained on MS-COCO dataset as our object detector, which is essentially a fast RCNN model with a segmentation mask prediction head. Since the backbone covenant of a faster RCNN rescales all input image to the same size, the part objects in the input image becomes too small in terms of number of pixels after rescaling. This makes it difficult for a model to detect them. We simply address this problem by sliding a window of size 400 by 400 over each original unscaled drone image and crop out the image. We let the windows overlap by 100 pixels so that a part object that is split into halves by the boundaries of one window can most likely be covered entirely by a nearby overlapping window. This ensures that each object is fully contained in at least one window. In total, we obtain 7,072 cropped images and thousands of annotations for the parts head, thread, nut, washer, and pin. We handle the class imbalance issue by giving objects from the rare classes higher weights when computing the loss function. During deployment, we feed all the cropped image patches to our model for object detection and finally merge the detections back to the original entire video frame. Once our mask RCNN model for detecting parts is trained, we expect that the weight parameters in its faster RCNN component has been well tuned to recognize the various parts involved in the target issues to detect. We can then get rid of the fully convolutional component for instant segmentation and continue to train the tuned faster RCNN network with new issue classification and box regression heads to obtain our final issue detection model. In this table, our model is named Tuned. We also trained another faster RCNN model, which is pre-trained on MS-COCO dataset, and call it Bayes. Recall, our model provides effective recommendation of potential issues for inspectors to examine further. Thus, we used two metrics. First is recall at K. Given the top K detections of an image with the highest probabilities, it counts the proportion of ground truth issues covered in top K. We can see that Tuned captured 71.5% of the issues, while Bayes captured only 59.6% issues, verifying the effectiveness of using part annotations initially to improve feature quality. A significant improvement can be seen even if we truncate the predictions to k equals 5 and k equals 10. Second is mean reciprocal rank, which computes the average of 1 by position. Here it is the position of a ground truth issue in the top K ranked list. As can be noted, Bayes has both MRR metrics between 1 by 5, implying that a true detection only appears after position 5, while Tuned has both MRR metric above 1 by 5, implying that a true detection often appears within top 5 probable predictions. This concludes our presentation. Thank you for listening. We're happy to answer any questions.